Marcus, you have the floor.
Thank you very much. Well, thank you for the invitation to join. My name is Marcus Munafo. I'm a psychologist based at the University of Bristol. I do both experimental and observational epidemiological work. And for a long time, I've had an interest in the factors that influence the robustness, the quality of the research that we produce. And that will be the focus of my talk today. Many of the examples will be from psychology, but many won't. And generally, they are from the biomedical sphere. So hopefully they will be relevant. Many of you will be familiar with the concerns that have been growing really over the last 15 years, that the quality of the research that we produce is not as high as it might be. And it was interesting, I think, to me that some of the first voices that raised that concern came from the pharmaceutical industry because of their experience of taking academic findings and bringing those into their drug discovery pipelines and finding that they were not able to reproduce those results in their own laboratories. So the pharmaceutical industry found that only about 40% of findings could be reproduced when they took those into their drug discovery programs. There were then a number of empirical attempts to estimate the proportion of published findings that could be robustly replicated in disciplines ranging from psychological science through to cancer biology. And interestingly, those different disciplines that have been empirically assessed all generate a broadly similar conclusion, which is that about 40% of our published findings are in fact reproducible. Now, it's worth noting at the outset that I don't think we should be aspiring to a world where 100% of our findings are reproducible, because we need to take a degree of risk. We need to push the envelope, if you like, in terms of attempting to discover new phenomena, if you like. And sometimes we will make mistakes in terms of what we hypothesized. But I think that 40% figure indicates that there is potentially some room for improvement in terms of raising the standard of the work that we do. So I'm going to start by talking about the experience in psychology. Then I'm going to talk about the factors that may be driving the problem, the mechanisms, if you like. And then I'll be talking about some potential solutions, including what I think is quite an exciting collaboration with a major cancer funder in the UK, Cancer Research UK. So in the reproducibility project that was focused on psychology, this empirical attempt to replicate 100 findings published in 3 major journals in psychological science, the key finding was that, as I say, only about 40% of those original studies could in fact be replicated. Now, these were good faith attempts at replication that attempted to replicate a key study as closely as possible, often working with the original study authors to ensure that the study protocol was a good faith attempt at replication of the original study. And what you can see here on the left-hand side are p-values for the original studies, nearly all of which were less than 0.05, and the replication studies, which were much more evenly distributed all the way through from 0 to 1 effectively. But perhaps more interestingly, on the right-hand side, you can see the effect sizes. And when you look at the replication studies, not only are the effect sizes systematically smaller in the replication studies compared to the original studies, but in some cases, the direction of the observed effect flips, what Andrew Gelman would call a type S or a sign error, as opposed to a type M or magnitude error. In other words, these are replications that show exactly the opposite of what the original study did, which is arguably more concerning. That would be the equivalent of a clinical trial showing benefit of a treatment, but then the follow-up trial, the replication study, showing potential harm of that treatment. So this was one of the pieces of evidence that suggested that the way in which we do research is perhaps not optimal, that the quality of the work that we produce could be improved, and that could be done by changing some of the ways in which we work. And as I say, that broad finding has been replicated across a range of different disciplines. So I don't think this is a problem that is unique to any one discipline. Having said that, I think there's a lot that we can learn from different disciplines in terms of what those individual disciplines do well, but I'll come back to that point later. But for me, a more interesting finding was this one. So in parallel with that empirical attempt at replication, some economists led by Anna Draber in Sweden were running a prediction market. And a prediction market is where you bet real money on future outcomes that have not yet been realized. And here, participants in the market were asked to bet on whether or not a particular study would in fact replicate. And the argument that economists make is that the fact that you are betting real money and the fact that it's a dynamic market, so you can buy and sell positions over a couple of weeks, much like you can buy and sell stocks and shares in the stock market, provides a better estimate of your true underlying belief, in this case, the likelihood that the study would in fact replicate. So the gray line on the figure is the 50% point, if you like. Above that, the market predicted that a study would in fact replicate. And below that, the study predicted that the market predicted that the study would not replicate. And the squares are what you need to look at. Those are the actual replication attempts. They only looked at a subset of the studies that were being subject to a replication attempt. And the black squares are the studies that did in fact successfully replicate, and the red squares are the studies that did not successfully replicate. In other words, you can see that above the line, the squares are predominantly black, and below the line, the squares are predominantly red. In other words, the market did a pretty good job of predicting the eventual outcomes with about a 70% accuracy rate. So in other words, although these were 100 papers that were published in good quality, high profile journals that had all been through peer review, the community had some sense, some pretty accurate sense of which in fact would replicate and which wouldn't. And I think that's interesting because it suggests that there is a great deal of knowledge that is hidden effectively, that doesn't enter the public domain. In other words, part of the problem is that what we see in the published literature is a very incomplete snapshot of the totality of knowledge that is generated by the scientific enterprise. And what we need to do is try to surface as much of that hidden knowledge as possible, so that in particular, early career researchers coming into science for the first time are better able to get a sense of what evidence exists, what evidence, how robust that evidence is, and so on. So what are the factors that are driving these problems? Well, I, as a psychologist, would perhaps not surprisingly focus on behavioral factors, because scientists, however well trained they are still human. And humans are subject to a range of different cognitive biases that psychologists understand reasonably well, that shape the way in which we see the world, interpret data, frame questions, go about answering those questions, and so on. This is a nice quote from Fooled by Randomness, which is a book by Nicholas Taleb. Scientists may be in the business of laughing at their predecessors, but owing to an array of human mental dispositions, few realize that someone will laugh at their beliefs in the disappointingly near future. And to give you an example of those cognitive biases, this is a photograph of a geological feature on the surface of Mars, taken by orbiting satellites at 3 different time points. The first picture, taken in 1976, looks like a face, and this became quite famous. A small number of people took this as evidence of intelligent extraterrestrial life, because it's simply too fantastic to imagine that this face could arise by chance on this distant planet. Except, of course, it did arise by chance. If you look at the photographs of the same feature taken at subsequent time points, it doesn't look anything like a face. It was a trick of the light, compounded by our tendency to see faces in inanimate objects. So people see faces in toast, in stones, in all sorts of things. And that's a cognitive bias known as pareidolia. And more generally, we have this cognitive bias of confirmation bias, where we tend to see what we are looking for in things. So as scientists, when we go out with a hypothesis and a strong motivation to discover things, which is well-intentioned, well-meant, we go into science because we are excited about our subject and we want to discover new facts or truths about nature, we can be led astray by that enthusiasm, by these cognitive biases. We can overly enthusiastically interrogate our data until we find what we are looking for, even if that thing that we think we have found is not genuinely supported by those data. So these are not malicious practices. This is honest endeavor on the part of enthusiastic scientists who can, because they're human, be led astray by their cognitive biases. So I think that's one mechanism that we need to think about. And then the other is the fact that we work within incentive structures, and we are incentivized to work in certain ways. We're incentivized to publish in certain kinds of journals, to publish often perhaps, to win grants, and all of these things can shape our behavior, again, in ways that we're not necessarily conscious of. And this quote from this survey that is quite old now, I think captures that quite nicely. Certain features of the working environment of science may have unexpected and potentially detrimental effects on the ethical dimensions of scientists' work. Not ethical in the conscious sense. Again, this is not something that would play out as malicious practice or fraud. This is honest scientists trying to discover things, but working in an environment that puts pressure on them to work in a particular way, for example, to find things, to discover things, to have statistically significant results, because those are more likely to be published in a certain kind of journal, support a future grant application, and so on. So this combination of cognitive biases and the incentive structures around us, I think, combine to create a situation where there are lots of behaviors that are quite common that are problematic. Again, not because they're conscious or malicious, but because we end up working in this way because we want to discover things and generate results that are publishable and so on. And this cartoon by the blogger Neuroskeptic captures this quite nicely, borrowing from Dante's Inferno. You have these different levels of scientific hell. And yes, at one level, down in the icy jaws of Satan, you have falsification, people faking their data. That does happen, but I think it's quite rare. What you have more of are these other behaviors that are not outright fraud, but are problematic in terms of the resulting robustness of the findings that we generate. So overly enthusiastically interpreting our data or interrogating our data, retrofitting our hypotheses to what we find, this post hoc storytelling that's known as harking, hypothesizing after the results are known, and so on. And so what we have is a scientific process that has arguably become distorted by this combination of a lack of protection against these cognitive biases and the growth of these incentive structures that push us in a particular direction towards, for example, only finding statistically significant results and therefore only publishing statistically significant results, which has a very distorting effect on what science looks like when you read the published literature compared to what you know science is like when you actually do it yourself. Now, we mustn't be too nihilistic. Of course, we continue to make progress. The scientific method continues to provide us with unparalleled insights into nature. But the question we should be asking ourselves is, can we do things better? Can we do things differently in a way that will improve the quality of our outputs and in turn improve the speed with which we can translate the knowledge that we generate into human benefit, societal benefit, health benefit, and so on. So I'll give you an example of what these different mechanisms, these distorting factors can have. So this is a study which recruited real participants and randomized them to listen to When I'm 64 by the Beatles or another type of music. And they found that those who listened to When I'm 64 became younger, not felt younger, but lost a year of life. And obviously, if that was true, that would be very exciting. This was an experimental study, so we can infer causality, except of course, that was a clearly false result. What had happened was that the authors had built enough flexibility into the design, conduct, and analysis of their study that they could effectively run a very large number of analyses, and by chance, one of those would generate a p-value less than 0.05. And you can see here, effectively, two abstracts superimposed on each other. You have the full abstract that shows all of that flexibility, and if you read all of that, you would realize that that final result was probably not robust. But there's also a redacted version shown in bold, which is only presenting the best case scenario, if you like, the most compelling version of the results possible. And if you read that, you might be more inclined to believe that that final result, perhaps not in this case, because it's so obviously false. But the point is, this study is structurally very similar to those that we see in psychological science and many other disciplines. 20 participants or subjects randomized into two groups with some primary endpoint. Now, the fact that that flexibility can lead to a false finding is not terribly surprising. I think what is more important from this paper is that it shows that when we read an abstract of a real paper, if you like, we have no way of knowing whether what we're reading is a full description of everything that was done or a redacted version that is giving us the best version, the most compelling version, the most convincing story, if you like. Because we rely on trust. We trust authors to give a full account of everything that they did, but the incentives are to give the most convincing account of what we did so that we can end up published in the types of journals that will advance our career. So at the moment, because we rely on trust, we have no way of knowing which version of the two possible abstract, if you like, we're actually reading. And we know that people build flexibility of the kind shown in that study into their study designs. This is a systematic review of functional MRI studies in humans. There were something like 240 different MRI studies included, fMRI studies included in the analysis. And Josh Karp showed that there were nearly as many unique analysis pipelines as there were studies in the sample. If you've ever worked with functional MRI data, you'll know that it's very high dimensional and it needs to go through a number of pre-processing steps before the primary statistical test can be applied to the data. There are something like 64,000 different permutations of different analytical pipelines available, creating a very large analytical space that can be explored. And if people are systematically trying multiple analytical pipelines and then only reporting the one that gives the strongest signal, that's going to systematically bias reported effect sizes away from the null and away from the true effect sizes. And the fact that there were nearly as many unique analysis pipelines as there were studies in the sample suggests at least a degree of that exploration of that analytical space. We also know that studies are often too small. And this was shown by Kate Button using neuroscience as an exemplar, but we've shown a similar pattern in a range of other biomedical disciplines. Studies are meant to have 80% statistical power, but on average, they seem to have something more like 20%. In other words, they're too small and therefore will give imprecise estimates. And therefore, those estimates are more likely to be incorrect, and statistically significant findings are more likely to be false when studies are systemically underpowered. But of course, again, if we think about this in terms of incentives, if you have 100,000 euros to spend on research, does it make sense to spend all of that on one study that will give you a very definitive answer, but where that answer may be null and therefore less exciting in terms of publication? Or does it make sense to slice those resources thinly and run maybe 10 smaller studies, each one of which would be underpowered, each one of which would be less likely to give a robust finding, but where by chance some of those findings will end up with p-values less than 0.05 and therefore be publishable. In other words, what is good for science is not necessarily what is good for scientists and their careers. And Malcolm MacLeod at Edinburgh has shown that we can't even use the institution, the prestige of an institution that a piece of work comes from as a proxy for the quality of the work that is produced. So this was looking at 3 different measures that protect against bias in rodent models. These were rodent models of or in neurological areas. And what he showed is that these things are generally not well reported, randomization, blinding, and sample size calculations. Just because they're not reported doesn't mean that they weren't done, but if they're not reported, we can't be confident that they were done. But the key finding really to me was that when you looked at the best institutions in the UK, according to our research excellence framework, which is this exercise that comes around every few years to evaluate the quality of research produced by our research intensive institutions, the studies produced at our best institutions were on average worse than studies drawn at random from PubMed. So if you look at randomization, for example, 50% of these studies in PubMed reported randomization, whereas only 14% of studies from those prestigious institutions reported randomization. And there is some evidence, again, for incentive structures playing a part, because when we look at countries with slightly different incentive structures, we see what look like systematic differences between those countries in the effect sizes that are reported. So, for example, in the US, if you are a full professor with tenure at a prestigious Ivy League department like Harvard, working in a biomedical research department, it may be that 0% of your salary is guaranteed and you only get paid if you bring in grant funding, which creates a very strong incentive to generate findings that are likely to lead to a successful grant application in future. And we find evidence that studies published in the US report larger effect sizes than studies published in other parts of the world. And if you look at other countries, you can see this direct financial incentivization of publication in certain kinds of journals. I would argue that that financial incentivization exists in all research systems, but is more explicit in some research systems than others. These are data from China, although this practice is largely being discontinued now, but until quite recently, the first author of a paper published in Nature or Science would receive a personal financial bonus for each paper published in those journals of over $40,000. And this, at the time, was set against an average annual professorial salary of $8,000. So these are life-changing amounts of money that are being offered for a single publication in a certain type of journal. The rationale being to drive publication in prestigious journals. But of course, that can lead to all kinds of problematic behaviors. And like I say, every research system financially incentivizes publication in these journals, because a postdoc with a publication in Nature or Science will have a very different career trajectory on average to a postdoc who does not have that kind of publication. So we assume that science is self-correcting, and of course, eventually one would hope that it would be, but the extent to which it self-corrects and self-corrects sufficiently rapidly is, I would say, an empirical question. We can't simply assume that science will self-correct. We can't simply publish papers and not be concerned about their quality on the assumption that someone will find the flaws further down the line. So is science self-correcting? Let's look at the empirical evidence. This is a review of about 80 articles published in the British Journal of Psychiatry, randomized controlled trials, and these 83 articles recommended interventions on the basis that the intervention showed evidence of superiority over the comparator, usually a placebo. Half of them hadn't been subject to any attempt at replication. Of those that had been subject to an attempt at replication, some studies did in fact replicate. Some studies suggested that the true effect size was less than the initially reported effect size, and some studies were contradicted by the replication study. Now, a single failure to replicate doesn't mean the finding is false, but it gives us reason to be cautious and indicates why we need to run replication studies to show that an observation of finding is robust. But critically, which category the replication study fell into was patterned by the sample size of the original study. So sample size of the original study is on the y-axis, and which category the replication study fell into is on the x-axis. And you can see that studies that replicated on average were larger than studies that were eventually contradicted. In other words, all other things being equal, larger studies will give more precise, more robust estimates. But as I mentioned earlier, the incentive, if anything, is to slice our resources thinly and run as many studies as possible. And in terms of the cognitive biases that I talked about before, there's also, again, empirical evidence that people interpret data through their own personal lens that can be distorting. So this is a nice example of that. The same data was shown to two different groups of people. So this was a heterogeneous meta-analysis, which one could interpret the results of slightly differently depending on whether one chose a fixed effects meta-analysis or a random effects meta-analysis, for example. People who had published in that area themselves were more likely to believe that a strong association existed in those data than were methodologists who had no personal investment in that study area. In other words, because we build our careers on the back of our own work and the work in the field around us, we become more likely to interpret results consistent with our own findings in a positive way because we have that personal investment in that topic. And here's another example of bias in the literature. So this is a citation network. The specific topic is shown on the left-hand side, but to some extent that doesn't really matter because this pattern, I think, is not unique to this particular area. What you have are a number of studies that emerged from the early 1990s until the mid-2000s. And there were two broad categories of studies, the primary data studies, and then the animal and cell culture models. The primary studies are shown in white, the animal and cell culture studies are shown in blue. And you can see that there were a number of studies in the early 1990s that generated the primary data, about half of which were critical of that underlying hypothesis and half of which were supportive. The supportive data were enough to give rise to the animal and cell culture literature, which took off in the mid-1990s. And what you can see are the citations. And nearly all of the citations were to the supportive data. There was only one citation to one of the critical studies. And that citation is shown in white because it's a critical citation saying there's this one study, but it's not very good. So if you are an early career researcher starting out in the animal and cell culture literature in the 1990s, the mid-1990s, you would believe from all the papers that you're reading that the foundation for your field is absolutely robust. whereas in reality, the evidence is much more mixed, because those studies that aren't being cited have effectively become invisible. One of the reasons why I encourage the use of systematic review and meta-analysis is that the systematic review methodology is explicitly designed to unearth studies that would otherwise be invisible if you just relied on the reading list, the reference list of published articles. So we have not only biases in publication, but also biases in citation. And that finding is, again, quite replicable. So here we looked at the association between the serotonin transporter gene and amygdala activation, working with colleagues in the Netherlands. This is a field that was publishing a lot of null results. It did quite a good job of publishing null results. So if you look at the inside of these figures, the studies themselves, about a third of the studies, maybe more like 40% of the studies were positive replications, so did in fact replicate the original foundational finding. About a third claimed to replicate that finding, but in fact, the evidence was a bit more equivocal. But about a quarter were explicit failures to replicate. They quite openly said, we failed to replicate this finding. So this is a literature where 1/4 of the published findings are null results. That's more than most literatures. But those studies that were failures to replicate only got about 3 or 4% of the citations. Now, we are incentivized by citations. Things like our H-index are driven by citations. So this shows why people don't write up their null results, because we know that if we get our null results published, they won't be cited as highly as our positive findings. So either we need to make our studies positive, these are the claim findings here, or we just don't bother writing up our null results and focus instead on our other findings, because we're busy and we need to decide how to allocate our time. But all of this, again, means that there are degrees of distortion in the literature, including publication bias, but also citation bias. And in terms of whether science is self-correcting, I think this figure demonstrates the scale of the problem. So these are 8 clinical trials of the same intervention for the same indication, so thrombolytic agents for the prevention of stroke. And over the lifetime of this literature, those 8 trials, 2 were positive and showed a benefit of the intervention over the comparator. 4 were neutral and showed no evidence of a difference between the intervention and the comparator. And 2 were negative. They were stopped early for safety concerns because the intervention seemed to be doing harm. And what you have is year of publication on the x-axis and cumulative citations on the y-axis. The first published study is positive, and people cite that very rapidly because it's exciting, it's good news, we found a new treatment. But then there are 2 studies after that that are neutral and 2 that are negative. So it's only by the time that the 6th published study comes along that we get a second positive trial. But it's not hard to spot that second positive trial because the rate of citation of that second positive trial is the same as the rate of citation for the first positive trial. And after only a few years, that second positive trial has been more highly cited than the 2 neutral and the 2 negative trials that were published subsequently. So does that look like science self-correcting? So again, the argument is that part of the problem is that we assume science will self-correct and therefore don't worry too much about whether or not our findings are actually wrong, because we're not incentivized as scientists to be right, we're incentivized to publish. So, the CEO of the CHDI Foundation in the US, which funds Huntington's research, convened this working group to discuss what we could do about this, and use the analogy of the US automobile in the 1970s. So in the 1970s, cars would be produced at a high rate in factories in Detroit, but the quality of those cars was very poor. Someone would count the number of wheels, and that was kind of it for quality control. And all of the quality control happened at the end of the production process. Edwards Deming, the statistician, took the concept of quality control in manufacturing to the Japanese automobile industry, where each step of the process was checked for quality. So you would make a small part, check that it was high quality, put it into the next larger part, check that that was high quality. And that produced much higher quality cars. The Japanese automobile industry still has a reputation for reliability today. But more importantly, I think, and less intuitively, Deming showed that by focusing on quality, not only do you improve quality, you also improve productivity, because you're not having to invest resources in fixing cars that broke down later. And that combination is why all manufacturing industries now use the same process effectively of quality control throughout the production process. So the question is, how can we embed those quality control checks throughout the research process rather than simply relying on peer review at the end of that process? And this is where I think open research has a part to play. Open research is this umbrella term for making all of the intermediate research outputs that are part of the research process, the data, the code, the materials, the reagents, and so on, freely available for reuse, but also for scrutiny. And if we take the example of data, the fact that someone can check your data not only means that that person might identify some errors, because in any human endeavor, there will be honest errors, there will be typos effectively, but also the fact that someone could check your data creates an incentive internally to make sure that we don't release anything until we're absolutely confident in the robustness of that output. And it also means that everything is made available, the study protocol, the data that are generated, the code, and so on, so that even if we don't write up the eventual results and publish them in a journal, all of that knowledge is in the public domain rather than hidden, going back to that problem at the beginning, that there is this knowledge that exists, but much of it isn't in the public domain. And what difference does that make? Well, if you look at pre-registration of primary outcomes in clinical trials as one example, in 2000, the National Heart, Lung and Blood Institute in the US required the registration of primary outcomes on clinicaltrials.gov for their grant-funded activity. And you can see year of publication on the x-axis, and the little flag is the year 2000 when that primary outcome registration was required. Now, before then, trials could be conducted and then written up for publication, and the authors could choose to change what they describe as the primary outcome and shift from what they originally thought was the primary outcome and effectively promote a secondary outcome on the basis of a small p-value. After 2000, if they did that, someone could find out because the primary outcome had been pre-registered before the trial started. Before 2000, the majority of studies funded by this institute showed benefit of the intervention over the comparator, and a few of the studies were null or neutral. After 2000, the majority of the studies were neutral, a couple showed benefit, and one for the first time showed harm. Again, going back to this point about the distorting effects of things like publication bias and citation bias and outcome switching, the problem is that the published literature is highly distorted. And that is what it looks like on the left-hand side of this figure, whereas the reality is very different. That's what it looks like on the right-hand side of this figure. And the problem for early career researchers is that their personal experience is like the right-hand side of this figure, but what they see around them in the published literature is on the left-hand side of this figure. So they think that they're not good researchers because they're not able to recreate what things look like in the published literature. But the problem is not them, the problem is the published literature. And I'm concerned that we might be losing very good researchers because they have that sense that their own work is not good enough, when in fact, it's perfectly good. It's the published literature that's the problem. So we published this Manifesto for Reproducible Science on the back of these growing concerns around the quality of published research, with a focus on what we could do differently to improve things. And there are a number of key stakeholders that have a part to play here. Researchers themselves, who can start to adopt open research practices, but also journals, funders, and institutions themselves. And we identified a range of threats to the hypothetical deductive model of science, and then different proposals for how those threats could be mitigated. So open research practices are one of those, but also different publishing formats, for example, registered reports, which I'll come on to in a moment. And there's been a great deal of interest in these issues in the UK over the last 5 to 10 years, with major funders like UK Research and Innovation, which is our major public funder, but also the Wellcome Trust, which is a major biomedical charity, publishing these reports that touch on these issues of research quality. And in 2019, we set up the UK Reproducibility Network to bring together researchers, institutions, and then other stakeholders like funders and publishers to work collaboratively, collectively, to identify potential solutions and set up pilot projects to look at how we could do things differently. So I want to finish by talking about one of those pilot projects. And this is the partnership with Cancer Research UK that I mentioned at the beginning, that takes the registered reports publishing model and integrates it with the grant review process. So if you're not familiar with registered reports, these focus on whether the study question is important and whether the methodology is robust. And the peer review largely happens before data collection begins. In other words, authors submit their study protocol effectively to the journal as a stage 1 submission, and the journal reviews that in a conventional way, but without any results, without any data having even been collected. One of the advantages of that is that that can serve to improve the quality of the study before data collection, rather than trying to improve it after the study's been completed. But it also means that authors then get in principle acceptance, which means that their study will be published irrespective of what the findings are, because the study has been designed to be informative irrespective of what the findings are. So in other words, if the question is important, then the answer to that question should be important no matter what that answer is. And because you have guaranteed publication in that journal, that then acts against publication bias, the tendency to not submit our null results to journals, and it acts against the temptation to overly enthusiastically interrogate our results, because we don't have to. The results will be published because the results are important, whatever they are. So that's the registered reports format. But of course, that's very similar to what grant panels consider when they consider grant applications. In other words, is the study question important, and is the methodology robust? So it felt logical to bring together a funder and a journal to look at whether or not those processes could be harmonized into a single process, so that at the end of it, you have funding to do your research and guaranteed publication of the results of that research in a journal. We started that with a small part of Cancer Research UK, the Tobacco Advisory Group, and a journal, Nicotine Tobacco Research, because there was a good match between what that panel funded and what that journal published. But we've now extended that to a much larger part of Cancer Research UK and brought in 12 different journals from Springer Nature, Wiley, and PLOS, including journals like Nature Communications and PLOS Medicine and PLOS Biology, journals that most researchers would be very happy to publish their research in. And the basic idea is that you integrate the grant review process and the journal review process. You can do that in a few different ways. There have been other smaller pilots. For example, the Children's Tumor Foundation worked with PLOS One, and there the primary review was done by the funder, and the journal simply agreed to publish anything that came out of that. Or you can do that the other way around. So CHDI, which I mentioned before, has been partnering with PLOS Biology, and there the journal can do the review. But the model that we have with Cancer Research UK is more like a relay race. The idea here is that it keeps the funder processes and the journal processes distinct and intact, so no one has to change how they work, which simplifies things for the funder and for the journal. But once the grant review has been completed, those applications that were successful are automatically handed over to the journal with the author's or the applicant's consent. And the applicants are then offered the opportunity to immediately submit a stage 1 submission. And the reviewers from the funder process can be invited by the journal to then review the stage 1 submission. The efficiency being that they've already read the grant, so actually they're already familiar with what they're looking at. And potentially, we know that reviewers of grants will hold back from making any critical comments if they want the grant to be funded, because they know that given how competitive grant funding is, if they say anything negative, it might mean that the grant doesn't get funded. But they have an opportunity to then say at the journal stage, given that the grant has been funded, I loved your grant, but I thought if you did this differently, it could be even better. And the study can be improved before any data collection begins. So it hopefully creates efficiencies and means that the applicants/authors then have funding to do the work and guaranteed publication in a journal of their choice by the end of that process. And it's easy for funders and journals to adopt this because their processes largely remain unchanged. There's just a bit of thought that needs to happen around how those processes are handed over from the funder to the journal. So it feels like a very exciting initiative. It's only just been through one round of a grant panel, but it will go through another round shortly. But the fact that we had major journals as well as a major funder keen to participate in that pilot, I think speaks to the enthusiasm of different stakeholders in the research ecosystem to take part in these kinds of innovative approaches, but also the level of concern that exists that we do need to do something to improve the quality of the work that we produce, and also incentivize some of these innovations by, for example, making it easier for people to use the registered reports format by linking it to the grant review process. So what I've tried to show is that there are these concerns that the quality of the research that we produce is not what it might be. some of the mechanisms of that are behavioral or psychological, effectively, but that there are a number of different initiatives that are being proposed to address those concerns, open research being one of those, but extensions to that, like the registered report submission format being another, which is now available at hundreds of journals. And some of the really exciting innovations will come about when we start to see these collaborative approaches between, for example, funders and publishers, as well as researchers themselves. Thank you.
Thank you very much, Marcus, for this really exciting presentation. I should...
No, you don't.
Okay. Yeah, I tried to switch on the microphone, but I don't seem to find the correct. Again, Marcus, it has been really, I think, complementary to the first talk. And it's interesting to see very similar effects in different observations in different domains. So now we can move to the discussion. And questions or comments from the public. Yes, please, Jose.
I'm going to start. The fact that this figure of 40% or so reproducibility seems to be across fields. What do you make of it? Do you think that the causes for reproducibility problems are going to be common across fields? I would expect that there would be like some specificities to fields, like the techniques we use or the objects we study. But if it's something that is actually more general, it would point more at the incentives or cognitive biases or things that are problematic across fields. So what do you make of that?
Yeah, I think that's a really good question. And I would agree with you that the fact that we see a degree of consistency across fields suggests that the underlying causes are probably common. And that's why I talk about things like cognitive biases and incentive structures. Having said that, I think we also need to look for fields that have much higher rates of reproducibility. So if you look at genomics, for example, that's a field that has undergone a transformation. So 20 years ago, people were doing candidate gene studies, and those studies were had very poor rates of reproducibility, with only a few exceptions. But then when we moved to whole genome approaches, genome-wide association studies, large international collaborative efforts, very large sample sizes, sharing data and code and so on, those studies are producing much, much more reliable results. So there are some fields that have gone through a change, and I think we can learn from those fields what the factors are that led to those changes. So it's not the case that every field is exactly the same, but there is, to me, a striking degree of consistency, which does suggest that at least some of the influences are general, because whichever field you work in, there is a degree of pressure to publish, for example.
Another question, a comment? So I will maybe follow up on the question from Jose. So this means, as you're saying, you're suggesting the cognitive, since we're all human, cognitive biases are influencing a lot our field of activity, which is research. And so isn't it kind of a pessimistic observation? And aren't we stuck in some sort of confirmation bias where we only, as you said, looking for information that is confirming what we're more or less we are already thinking? And since it is common to everyone, can we get out of it?
Yeah, well, I mean, so I wouldn't say that it's pessimistic necessarily. It's just a feature of being human. You know, we have to accept that we are all human, and training is not sufficient to protect us from these cognitive biases, because they operate automatically and unconsciously. But what we need to do, by having recognized that they exist, is put in place protections against that. So to give an example of one of those protections, pre-registration of study protocols, that's something our research group has been doing for several years. And what we have found in our experience is that you design your study and then you may have the data a year later or even further along than that. And when you get to your data, you're very excited to analyze your data. You start analyzing it. You see things that then make sense. And so you think, well, we must have thought that we would, I don't know, test for sex differences. But then you go back to the study protocol and you realize, oh, we didn't think that a priori, or at least we didn't write it down. It doesn't mean you can't do the analysis. You just do the analysis explicitly as a post hoc analysis that was informed by the data. But it illustrates how easy it is for us to be fooled if we don't have that pre-stated outcome and hypothesis that we lay down at the beginning of the project. So those open research ways of working are just a way of protecting us against those cognitive biases. They're not meant to stop us from doing anything, but just to help us be more explicit about what we really did hypothesize a priori versus what is more exploratory work that came up post hoc.
I will allow myself to make a comment on this, and this is related also to the example that you provided about the car manufacturer.
Sorry, I didn't hear that.
It's related to the example that you mentioned about car manufacturing, and how it has been, the quality control has been incorporated in the process at every step. And as you know, in different industries, there are now not only car manufacturers, there is a lot of norms that are a lot of them are international, like ISO, normalization. Yeah. And at least in France, I don't know how it is in the other countries, but in France, there has been in the recent years a push to create norms for research process. So there is a French norm for research and they fix something, I don't remember the number. There is a push from the institutions such as Ministry of Research to try to provide incentives for scientists to get certified by those norms. However, as far as I can see, and it's not a study, but it's just a personal observation, in research, this receives an extremely negative reaction, and people are saying, "Oh, I really don't want to hear about that in the lab. This is for factories and things like that. It's not for my creative process." You see what I mean? So
yeah.
You can comment on that?
Yeah, I mean, it's a good example of how we need to strike the right balance, I think, because it's true that different research groups will do things very well. They will have good standard operating procedures or whatever it might be. But if those are all slightly different, that creates a degree of inefficiency, because if you are a postdoc working in one lab and you learn how to do things in a certain way, and then you move to another lab, you have to learn things in a different way. So a degree of standardization, I think, would be valuable. And I think it would also help with transparency, because it would be easier then to share data, protocols, materials, SOPs, and so on. So I do think that there is value in a degree of harmonization. But of course, one of the problems is you don't want to homogenize the whole discipline so that everyone is working in exactly the same way, because then you have no space for innovation. So there needs to be a balance between the two. One of the things that we're doing in the UK is running train the trainer courses on open research practices. The idea being that people come in from different universities, departments, research groups to learn how to deliver training in open research practices, but then can tailor the workshop that they deliver to the particular audience so that they're not all exactly the same, but they share all of those workshops that are then delivered, share some commonality because they all come from the same train the trainer course. So I think we can find ways of making people work in more interoperable ways without imposing excessive standardization.
Yeah, Jose?
Yeah, I have a question about the pre-registration initiative that you mentioned. I see how that works for clinical trials and preclinical trials where you pre-register your experiments. I was wondering what you think how's that going to work for more fundamental questions? I'm thinking of biology here, where a lot of the work is exploratory. You mentioned before the post-hoc analysis that you might come across, but I wonder if trade registration also applies with this context where you have to do a lot of searching around to see what is worth pursuing as hypothesis, or for example, maybe introduce some rigidity to the scientific process if a big part of the work is pilot or exploratory.
Yeah, I mean, that's another really good question that comes up a lot. People have slightly different views on this. My view is that the main value of pre-registration is transparency, and you don't necessarily need to go down the route of a registered report. I agree that the registered report publishing model works best for experimental studies with a clear hypothesis and a clear primary outcome. But it can be more flexible than that. But pre-registration more generally, I think is just laying out in advance what you plan to do and how you will do it, what you expect to find, if you expect to find anything, or if it is truly exploratory, making it clear from the outset that it's truly exploratory. I think one of the problems we have is that we almost fetishize confirmatory research at the expense of exploratory research, so that by the time we get to writing something up for a journal, we have to pretend that everything was confirmatory, whereas in fact, exploratory research is really important, but we don't feel able to say we just did some exploratory work. So I think pre-registration can help us to be transparent, and we need to be more honest about when we are doing truly exploratory research, because I think that's valuable, and we need to make it clear that it's valuable by not pretending that it was confirmatory when we come to write it up.
Yeah.
Thanks for the presentation. About the figure you showed rather in the beginning about the prediction markets, that seemed to show that scientists have overall a pretty good sense of which results they can rely on and trust and which they cannot. And isn't that in tension a bit with the claim that science doesn't self-correct? Because it would suggest that scientists pretty much know which results they can base their future work on.
Yeah, I think that again is a really good question. I think you're right in the sense that scientists themselves have a better sense. It wasn't a perfect prediction, that's worth noting, have a better sense. But of course, many of the end users of scientific research are not scientists. They're politicians, policymakers, healthcare providers, the general public. And those people only have the published literature to go on. So the published literature is the part that is perhaps not self-correcting as rapidly as our sort of hidden knowledge that we have as a community of researchers. I think it's also a problem for early career researchers, PhD students. You know, my experience as a PhD student, the first experiment that I ran was a replication study of a finding that looked absolutely robust based on the published literature, which as an early career researcher was all I had access to. And I couldn't replicate that finding. And so I thought, well, maybe I'm not cut out for a career in science because I can't replicate this really robust finding. And it was only because I was lucky enough to meet a senior academic who said, oh, no one can replicate that finding. Everyone knows that. Well, I didn't know that because I'd only just started in science. So I think we risk losing people because they have that kind of experience. And lots of PhD students and postdocs have said to me that they had a similar experience. If you're not lucky enough to meet someone who has survived in the system long enough to gain access to that hidden knowledge, then you might leave science, leave academia, and we could be losing good people just on the basis of bad luck. So I think you're right that the reality within academia and the research system is slightly different, but that the problem is still real because of those two other different parts. The fact that the end users of research are often not scientists, and that early career researchers don't have access to that knowledge unless they can stay within the system long enough.
Okay, so thank you very much again. I think the two first presentations gave an excellent transition for the talk of Frédéric.